back in time. Okay. Hi, everybody. My name is Tonio Buonassisi. I'm joined by Raul Ortega-Ochoa today. We're at the Materials Innovation Factory at Liverpool. Materials Innovation Factory at Liverpool seminar series organized by Vitaly and colleagues. Really a pleasure to be here. And today's topic is on materials representations, meaning how do we represent a material to a machine learning algorithm to perform either property prediction or inverse design. And maybe, Raul, if I could invite you to go to the slide 2, the one with the green on it. Yes, perfect. What is a material to you? We just had it appear briefly on the screen. The screen turned black.
Yeah, it's black. It's black on my side too.
Okay, perfect. We're working through the screen difficulties at the moment, but the key message in the slide is think back to when you were trained as a physicist, as a chemist, as a scientist, how you were taught what a material is. When was the moment that you created in your mind a model for what a material is? And many of us, for many of us, it happened somewhere between our elementary, high school education to our beginning years as a graduate student. And a ball and stick model appears in our heads, right? When we ask, what is a material? So for me, it was very clear. We were shown pictures of atomistic models of crystals during my high school chemistry. Then as an undergraduate, I was introduced to the basic principles of solid state physics. The representation of a crystal as a ball and stick model appeared. We solved band gaps for gallium arsenide using group theory in Stephen Lewis' class using Charles Cattell's book, the green and blue books. And then finally, density functional theory approximations took that same realm of concepts and enabled us to perform numerical solutions on much larger crystal models. So this was how I was trained. I imagine you were trained in a very similar way. And so the prevailing bias going into machine learning is that you need a ball and stick model. You need the elemental constitution and you need the structure as inputs into a machine learning model in order to predict properties, in order to do inverse design. And I'm going to put a flag right there and come back to it in a few moments. But now let's challenge that underlying assumption. Why is it that instead of just the elemental constitution and the structure, why is it that we don't also need the chemical information? Why don't we need to know the ionic state of those atoms? Why don't we need to know other properties? And maybe going the opposite direction, why do we really need structure? If structural information is somehow embedded in the valence state of each of the atoms inside the material, do we really need to know the structural information explicitly? Or is it enough to know the elemental constitution in the material? And what I'm trying to do is weaken those underlying assumptions in your mind about understanding what a material's representation is and should be, and recognizing that some of that is coupled to our own training, right? There is an event stream dependency here on how we, in our minds, represent materials. So if you go to the next slide, Raul, thank you. It looks like we're up and running. Thanks for your efforts there on the backside. The next slide is basically just, many societies a few thousand years ago had different materials representations. In the case of the Greeks, the idea that water was comprised of air, fire, earth, and air, fire, earth, and water. You might say, well, that's ridiculous. I mean, they knew about amber and about charge. In fact, the word electron derives from there. So why is it that how does an amber crystal somehow relate to these different elements? It's not that it's fire. You touch it, it's not hot. Yes, okay, we can critique easily representations from a few thousand years ago because the people who developed them aren't there to defend those ideas. But then why do we have confidence ourselves that we've converged on the final best representation of materials in 2025? Why can we also not have a certain amount of humility and hold that in view as we move forward? So next slide, please. This is, this is essentially the representation that many of us hold in our minds, either a simplistic ball and stick model or some information about the valence band maximum, conduction band minimum in materials that, or let's call it highest occupied, lowest unoccupied states in materials that are participating in charge transport, in optical interaction with optical photons, and so on. So next slide. You know, we get even more complicated here. We have CIF files, we have band structures, we have processing conditions used to make materials, and we have the defect structure in those materials. We have interfaces. There are many additional properties that one could argue should feature into the representation of the material, because those properties may be deterministic of the ultimate observed mechanical, electrical, optical properties in the material. Okay, with all that background said, we're going to move on to the next slide, which is now, let's shift our perspective from the human, where we planted the flag, to a machine learning algorithm. Next slide. Alex Zunger, formerly of NREL, now in the Colorado University system, I credit as being one of the first people to articulate the concept of inverse design and the importance of a materials representation in that. So in other words, how do you represent into an algorithmic form, whether it's simple, let's call it simple computational property prediction, or some of the more emergent inverse design algorithms, how do you represent materials into these spaces? So that's the essence of this slide right here. And if we move to the next one, we'll start to provide a little bit of background. So this question about what is the necessary and sufficient information to include in a materials representation was first articulated by several groups, including ours, a few years back. And next slide. I'd like to borrow an analogy from the Zillow, not Zillow. This was a random forest regression algorithm training set to predict property prices, right? So if you can imagine, Kaggle had a data set for training machine learning specialists to perform machine learning algorithms. You had perhaps on the order of 70 features, the square footage of the house or square meterage of the house, the area, in other words, the area of number of bedrooms, the number of garage spots, covered garage spots, location, and so on. So about 70 features and 1,000 entries into that data set. And it turns out that if you're trying to predict the price, the selling price of the house, you don't need all 70 features. You only need a subset of them. And these are things like location, number of bedrooms, and so on, right? So it's a shift in perspective of more data is better. When it comes to input features to determine a certain set of output properties, you need the right input features. The remaining features, the nuisance features, if you will, simply add noise, they add uncertainty, and they increase the odds of overfitting locally to a certain set of input data rather than the global output features. They don't generalize well. So with that background, next slide, please. Next slide, I'll skip that for a moment. We turn to this idea that the materials representation is best described using a combination of elemental composition and structure. So this idea of elemental composition and structure originating from density functional theory calculations and from our background in solid state physics was put to the test a few years ago by a researcher in my group called Isaac. And Isaac was really trying to understand, can I turn these features on and off selectively? Can I, for example, use Roost and CrabNet to compute or predict properties like formation energy per atom, band gap, mechanical properties, density? Can I use just the compositional information? Or do I have to use the elemental composition and structure? Do I gain some predictive capacity? Can I reduce my root mean squared error in predicting these parameters by having machine learning algorithms that incorporate both the elemental composition and the structural information, which we call compstruct. And those include algorithms like MagNet and CGCNN. And a few different ways to slice your data set. You can look at polymorphs or just the compounds that are within a few tens of MeV per atom above Hull. Those would be called the stable. Let's make an arbitrary cutoff at 100 MeV per atom above Hull. Yes, I know about the amorphous limit, but for purposes of broad calculation, let's do a simple metric here. And this analysis on the next few slides revealed that, it revealed essentially that in many cases, just the elemental information was necessary. So let me quickly review the way that certain information is contained in the CGCNN model, because this will be relevant to the slides that Raul will present later on. So in a CGCNN, in the simplest version that was published by Tien Xie and Jeff Grossman, Tien, by the way, is now at Microsoft with the latest releases of the property predictor, and Jeff Grossman is still at MIT. In the earliest versions, the nodes represented the elements and the edges represented the connections between them. There was no information embedded in the edge in the earliest versions of CGCNN about distance or angle. It was simply connection. And in more recent versions, the CGCNN framework has been upgraded to include angle and distance information in the edge. And so the CGCNN structure information can be really as complicated as you want it to be. It's really just a matter of encoding. And so Raul will return to this. And what I want to highlight is you also have the option of going the other way. In the edge of the graph, essentially the connections between nodes, you have the option of setting every edge to 1, thereby eliminating the structural information, right? So if if everything is set to 1, there is essentially no unique information, no preference about how the atoms are connected or oriented inside the crystal. So we'll return to this CGCNN framework when it comes time for Raul to present his computational results. And we'll continue. Next slide. Yes. And just a quick note about composition only. It was very interesting. If you go back to some of the earlier papers, for example, about Roost or other frameworks, the number of data or number of training epochs needed to reduce the RMSE error was actually quite small. If you look at the number of epochs, or alternatively, if you look at the amount of training data, in many cases, it was order 100 for the mean average error to drop to some plateau value, depending on the complexity of your model. And I want you to file that piece of information away. Decent property prediction of materials using composition only, it can be achieved in many cases within about 100 training epochs. Next slide, please. This paper. Okay, so Ichiro Takeuchi, a quick hats off to Ichiro. He was recently elected a fellow of the Materials Research Society, and for a very good reason. Out of his group at University of Maryland have come a series of applied machine learning people, including J. Hatrick Simpers, Brian DeCoste, Gilad Kuzne, and many others. Really an exceptional research group and a lot of gems that are, in my opinion, criminally undercited. And one of the papers that was published by their team in 2018 was a pretty decent prediction of the Curie temperature, essentially the superconductivity transition temperature, using just the chemical formula, just the pretty formula. So just elemental information and stoichiometry. And for me, that was really impressive paper. There were some difficulties generalizing outside of specific materials classes, as shown on the right-hand side, but in general, the global model did rather well. And this was the initial trigger point that led me to explore this question of what is the necessary information that must be contained within a materials representation to predict properties. Next slide, please. All right, so I promised you the results from Isaac's study, and here they are. This paper is on arXiv. If you look up Tien and Buonassisi, you'll find the link, or if you copy that link at the bottom of the screen, you'll also find it. No matter how we cut stable or unstable compounds, meaning a certain delta, 100 MeV per atom above Hull, the improvement of mean average error of predicting properties shown as columns here, formation energy per atom, band gap, mechanical properties, density, and point density, the predictive accuracy did not improve substantially by the addition of structural information on top of the compositional information until we got to certain properties like point density. Now, point density is literally the number of lattice sites per unit volume, right? So it's essentially only a property of the structure. There is no elemental information at all. One could argue that even density, like the grams per cubic centimeter, is affected by the Z of the atom, right? So if you have a heavy atom like lead as opposed to a light atom like lithium, the density will be directly affected. But point density is not affected by the elemental number or Z. So it's only when you get to point density that you see a substantial improvement to the predictive accuracy. And for many properties like band gap, formation energy, and even mechanical properties, it was astoundingly similar how well one was able to predict those properties using only compositional information, or alternatively, how little additional value structural information gave you. Next slide. Polymorphs were explored as well, and these likewise did not give a significant improvement. If we keep moving forward, let's move to your slides. Oh yeah, okay, this is good. This is actually back one, sorry. Back one more. So the world model that emerged from this study that included Aaron Walsh from Imperial, next slide please, sorry Raul. The world model that emerged was the following, that the observation that in many cases, compositional information yielded similar predictive properties to compositional plus structure, is that in many cases, the property is the compositional information embeds the structure. In other words, there's some self-consistency between the compositional and structural information. And this was the background or the foundation upon which Raul began to ask some deeper questions about materials representation. So I think at this point, Raul, I'd like to advance to your slides and hand it over to you to talk about where you picked up and some of the insights gained over the course of your project.
Tonio, thank you. I hope it's okay for you in the car, so because you were driving, right?
I'm not driving right now. I'm pulled over to the side of the road.
Okay, great.
The emergency blinkers are on. The car is in park.
I see.
Everything is fine.
I see. While Raul going to the slides, could I quickly ask about diamond and graphite?
Yes. Well, not only diamond and graphite, but carbon nanotubes and glassy carbon, coal, right? You have many different forms of carbon. Yeah, and so there were cases point by point, right? You can always find exceptions to these where there's big differences, right? So for example, moving from a semi-metal, which could argue some of the forms of carbon are adopted, right? Where you have no separate, you have zero density of states, but almost no separation between valence and conduction bands, moving all the way to a band gap of what, 5 eV or so. So yes, there are cases when you can pick out single cases that defy this rule. But if you look at the ensemble, the average, in many cases, you land in similar ranges. Yeah, and so great point. You can always find exceptions to almost every rule you put out there.
Okay, thank you, Tonio. Feel free to continue.
All right, thanks. Yeah, so yeah, as Tonio pointed out, when I started working with his group is when I came to know this paper with Isaac, Antonio, and where they at the end of the paper they hypothesized that composition embeds structural information of stable monomorphous compounds, which is a fair assumption. It's a fair hypothesis. But then I think I started maybe also asking some other questions, right? So this came from, so I think this project that we're talking about today, I think came from different points, right? I feel like it was the merging of different perspectives that we have been developing. So I think one of the early things that I tried to do was like, given that this was the hypothesis that, you know, compositional embedded structure of ground state and stable configurations, could I also train a model just on structure without composition? And because that would be also trying to prove that there's a regime, there's a subset of materials that can be uniquely maybe defined, at least in terms of information, using only the structure without composition. But yeah, we started asking some more questions because I have the feeling that well, machine learning algorithms are like black box models, right? And we've seen that surprisingly, like really simple representations that coming from a physics point of view wouldn't make sense. Like there shouldn't be enough. It's just how can it be that they perform on par with some more what we think is richer representations? So that's what got all of this started. The apparent contradiction or break between what we think is a good representation and how ML models or these data-driven approaches can do well, like reasonably well, with really poor or simple representations. So yeah. So perhaps if you're familiar with the paper we put in archive, I think first we need to define what we mean by poor and rich. I think under the hood, what we mean is that it's information wise. So we think that, for example, the CIF file for a crystal is a relatively rich representation because it contains a lot of information about the material. And for example, composition is poor because it's a information wise poor in the sense of it doesn't contain as much information about the material as the CIF file. And equivalently, we can think of information as the reduction of degeneracy or the reduction of redundancy. If we only specify the composition, we have different possible spatial arrangements of atoms given that composition. So that's what I mean by degeneracy. So the fact that there's more degeneracy means that there's less information. So the other way around, sorry. Yeah. So basically, maybe a simplified version, simplified perspective of materials could be materials proper. We could say that there's like something that is the material, there's something that is representations of material, and there's things that are properties of materials, right? Maybe that's a simplified version of it. And I think from our physics intuition, we tend to think that the representations of the material are actually the material. But that cannot be the case, right? We cannot say that both the composition is a representation of the material, or we cannot say that a representation is the material, because otherwise we would be forced to say that composition is the same as the CIF file, right? And it's clearly not. There's like a gap of information between them too. So therefore, that's the first thing, like differentiating that, no, a representation is not the material. So upon thinking about this is what led us to think about the material as something else. And since it would be really hard to define a material intrinsically in these terms, what we thought is, okay, let's put the material as a intangible, separate object that is only accessed through its properties and its representations. So basically what we say is that a simplified view is like, we don't see the material. What we see is its representations and its properties. In the same way, we see the shadows of an object and not, like in this image, we see the shadows of the object and not the object itself. And then that led us to question also, like, what do we mean by when we say something is a representation, or when we say that something is a property? So we tend to think of a property, at least in machine learning terms. We could say that the material, so the material is something, right? And then a property is the result of a function that may be unknown in general, acting on the material. So the property is a function of the material, even though we don't know this function. And then what we do in machine learning is basically train a parameterized function to approximate this unknown function by minimizing the difference in the predictions between the known and the unknown function. Basically, we create a surrogate function, right, that approximates the unknown function. So that's how we tend to think about properties. But then when we started writing down the equations, we realized, okay, but what is the difference with a representation? A representation is also a function of the material because a representation cannot contain more information about the object that represents it. Therefore, what is the line that divides what we call a representation and what we call a property? So we started to question this line because this line started, when you think in these terms, the line becomes really blurry, I think. There's no point at which one would say, oh, this is a representation and this is a property. So then we would say, since we cannot draw the line, we might as well say that we can say that a representation is a relatively rich information-wise property, or a property is a relatively poor representation of the material. And I think this was a satisfying moment when we realized that maybe, because if we remove that line between what constitutes a representation and what it constitutes a property, then this terminology of forward and inverse design that we use in materials and ML for materials, it starts to blur with it. Because if both are just properties, or we may as well call them projections of the underlying material, then there's not that much difference between them. Maybe a note on that. Actually, I think there's a relatively distinction between what we tend to think of a representation and a property. I think representations tend to be more informative. But the problem is that the line is not drawn. But yeah, we can talk about that more later. So that led us to draw these pictures, which I've seen that some other people have found some other connections to some other areas, given these pictures. So basically, the idea is that we have this material thing, which is the cylinder, right? It's a higher dimensional object, and we only see its shadows. And the thing is that shadows, which could be representations or properties. And the thing is that not every property adds the same amount of information, right? And not only that, but there might be properties that are already embedded in some others, in the sense that if you see so figure B, you can see that, for example, if we add another property, which is F3, the function 3, then that doesn't add more information about the underlying material. Yes. So yes, so then we wanted to also delve deeper into this, right? Because what we've seen that this is an empirical result in machine learning for materials, that there's two innovation directions, maybe in a simplified view again. One can enhance the architecture of the model. That's the skeletons of the model. And then the other direction would be to enhance the representation, enrich the representation. And something that some people have been doing for some time is, given the same architecture, more or less, or the same overall architecture, what they were doing is expanding the representation. How were they doing it? So they have seen that empirically, when they added some other properties on top of their graph or whatever, some properties that are related somehow with the ultimate goal, the predictive power would increase, but only sometimes, not always. So then we try to also delve deeper into how could this happen. So this has to do again with this figure, right? Because if we add, so we try to explain how can it be that sometimes this works and sometimes it doesn't. So it's under the hood, so everything is about information, right? So there's a extension of information theory that deals around mutual information and mutual information of several variables, right? I think something that is particularly interesting is to try to decompose the mutual information of several variables into the unique parts, the synergetic parts, and the redundant parts, right? So it's a framework which is called partial information decomposition. I recommend that you take a look at it because it's really interesting. And yeah, so what we say is that we hypothesized and then we verified it, that basically when we are adding a new property to the representation that has to do with the ultimate goal, you know, what we're adding is extra information that is unique and was not already embedded in the original representation. Because if it was already embedded in the original representation, we would get no performance improvement, right? And if it's, yeah, so even if a property is related to our task, if that information was already in your graph, in your previous representation, you would not see an improvement. Well, okay. So then we wanted to assess mutual information between several variables for the materials project. So we wanted to see which properties are interlinked, right, or share information. The problem is that perhaps someone will come up with a better solution. Estimating mutual information is a hard thing. And it's a hard thing, and especially for higher dimensional things, for higher dimensional data, which is the natural regime of ML. So there are some methods, there's Kraskov and some normalized mutual information, but as far as I've seen, they don't scale well for higher dimensions, which is again the natural regime of ML. So what we assess, what we try to do is we try to assess the mutual information between two things or quantify it somehow through a proxy variable. And this proxy variable is feature importance. Why? Because I mean, the importance of a feature for some other task depends on the mutual information they share under the hood, right? So we can think of maybe perhaps 4 cases, right? If we add a property A to property B on top of our representation, if property A embeds important information, maybe we should expect that the performance improves. But if that information was already encoded in the original representation, we see no performance improvement. Yeah. So this is what we tried to do here. So basically what I took is I took CGCNN, which is a standard model, right? That everyone, you know about it. Yes, and what I did is I augmented the representation. So we added a property into the latent space, and we would compare the normal behavior of the model, like the normal performance, versus the enhanced performance. That is, it was all to answer one question, like, if I add this property to this model, do I get an improvement in performance? If so, that must mean that this new property that I added is not only important, but it was already not accounted for. So I trained a bunch of models on all possible combinations of different properties. And yeah, exactly. So this is a schematic of how I created the experiments. So one is the normal model and one is the augmented model. For both of them, I compute the same property, and then I check the relative change in performance. And now that I add into one of the slots in the heat map. So these were the results, for example, for the normal CGCNN, that is which is the model that takes into account both composition and structure, because it creates a graph based on distances. So it has distance. It has some notion of the structure of the crystal. So maybe it's worth highlighting some patterns. We can discuss it later otherwise, but like, of course, you see that this diagonal here, of course, because if we feed the property that we want as target as input, the performance, of course, increases, the error decreases significantly. So that's what you see here in this diagonal. But then maybe that's something that was particularly interesting was the fact that this matrix is not diagonal. That is that adding, so say you have your graph, you have property A and B. So A is more important for predicting B, given the graph, than the opposite. And this is something that you can explain. It could be synergetic behavior, and you can explain it using the partial information decomposition within this framework. Yes.
Could I ask about the numbers in the table?
Yes.
If you could clarify, are these percentages or errors, or what do they represent?
Yes, so they are percentage in the reduction of the error. Yes, that's a fair question. Yes. So basically, for example, if I'm gonna predict here, I don't know if you see my mouse, but if I am going to predict the band gap, and I give us extra feature band gap, I get a reduction in the error of 97%. fair, right? I'm feeding the solution. Maybe we can see others that are more interesting. For example, if I'm going to predict the energy and I give on top of the graph representation of CGCNN, I give the space group number, I get a reduction of the error of 7%, around 7%. That's what it means.
So these minuses are reductions in relative errors.
Yes, reduction in relative error. And actually, is the mean absolute error on the test set.
Okay, thank you.
Yeah, fair question. Yeah, thanks for pointing it out.
And Raul, the asymmetries are really interesting, right? So magnetization and energy per atom, for example.
Magnetization and energy per atom. Yeah, exactly. So sometimes you would see like huge asymmetries. For example, I think this is one case. So, yeah, I mean, but there are several examples of such thing. I don't know if it's worth going into the details. Maybe we can go later into the details, or if someone is interested. The thing is that I did this same experiment for both a model that for both CGCNN with structure and without structure. So maybe I can show that those results here. So on the
Raul,
left, you have.
Sorry, Greg, do you have a question?
Sorry.
Are you sharing your screen right now?
Am I not sharing my screen?
I see the screen. I see the screen.
Greg, it's still maybe not the full screen mode, but we can basically see the slide in full. Yeah.
I cannot see the slides. I do not know.
And what do you see, Greg?
I can see, I can switch to gallery. I can show speaker. On video show meeting times. I do not see the screen. Does anyone else have this problem that they cannot see the screen?
No, I'm able to see Raul's screen. What I can offer to do is the chat. So you can follow along seeing the chat. Does that work?
Yeah. How about Vitaly? Can you see the screen?
Yes,
okay.
I can see the screen, although it's not full screen mode, but still okay.
Yeah.
Generally.
Yeah, it's because of the.
Yeah, probably we could continue, and hopefully the recording will show the screen as I can see it right now. Yeah,
perfect.
Thank you.
Thanks. Yes. So the idea is that given these heat maps, basically we can see like a pattern of which properties are contained within which others, right? And then I repeated this experiment. So CGCNN, as Tonio pointed out, takes into account the geometry of the crystal, and it does that because it perceives the graph. And then it perceives the graph given on distances. So there's under the hood, there's like distance. There's like a notion of the spatial arrangement of atoms. So then I wanted to do the same test, like seeing which properties are important when we don't have a structure. And for that, I wanted to use the same model. And why is that? Because if we change the complete architecture of the model, then the patterns that we see, we could blame them on the architecture and not the representation. I don't know if that makes sense. Because I wanted to compare representations, I wanted to use the same model. Otherwise, one could say that the differences I see are due to the architecture and not the representation. So basically that's why I kept the same model. And the way I fooled CGCNN to not know geometry was by fooling the perception algorithm. So as Tonio pointed out, like CGCNN based on distances, it creates a graph of the crystal. So basically what you can say is that everything within the unit cell is connected to everything at the same distance. So, if everything is connected to everything, nothing is connected to anything in the sense of geometry has been removed effectively. And then it's interesting to compare the results. So like we can see some global patterns. For example, something that is pleasing because it fits into our physical intuition is the fact that, look, when we remove the geometry and then we feed things related to geometry, for example, I remove the geometry and then I say, okay, you have the composition plus a space group number, and it helps a lot. Nice. I have the composition plus space group crystal system, and it helps a lot. of course, because I'm feeding again the geometry. But if you compare that before, those features did not help a lot. Why? Because they were already accounted for. That's the intuition behind this. And well, maybe to summarize, because I've been talking too much, maybe. So I think what we proposed in this paper was like a conceptual framework of thinking about materials representations and materials in general within the machine learning context that I think solves some mysterious behaviors that we had seen empirically. For example, I like to outline, for example, this quote from I think it's in the abstract actually, of this paper, which is recent also. They say, we've hypothesized that the property to structure mapping becomes unique when a sufficient number of properties are supplied to the models during training. This hypothesis has several important corollaries if true. It would imply that data scarce properties can be completely determined using a set of more accessible molecular properties. In this case, works for molecules, but I think this is especially revealing, right? Yes, this is the case because properties capture information about the underlying material essence, and representations of property are more close than we thought they were. And with this, I'm done with my part.
Right. All right.
Thank
Thanks, Raul. I think maybe there's a couple more slides, maybe one or two left in the talk. Yeah. So more key insights just to really get connections moving, because I'm speaking to a group of experts here. In the FDCP model, which we published a few years back, there was a matrix portion in the input feature representation highlighted in red on this slide in the middle called elemental property matrix. In the code, it's abbreviated LMProp. I hated this. And Danny and Isaac came to me and they said, but it improves our predictive accuracy when we include certain properties of the elements in the input representation. Things like the electronegativity, atomic radius. I said, I hate this, guys. Atomic radius. I mean, pick sodium, for example. If it's in the neutral charge state or the +1 charge state, the radius is changed by almost a factor of 2. What parameter are you going to pick? And they said, well, look at the results, Tonio. Don't be so close-minded. We're improving predictive accuracy. Now, based on what Raul did, I know that based on partial information decomposition, I know there's some additional information embedded in those features that was not being represented in composition and structure alone that somehow linked to reduction of some error. And FDCP is complicated, right? It's a VAE, so I don't know if it was training error or sampling error in the latent space or reconstruction error. I just don't know. But somehow the system improved from an information theory perspective. We were adding more useful information to the system through this LMProp matrix. Next slide. I still hate it, by the way. But I'm more of a purist in that regard.
So
Next
what
slide.
what radius was taken, Tonio?
Elemental.
Okay,
Yeah,
so
it
there
was
is some.
just pure neutral charge state, a
Okay.
neutral elemental radius, not the ionic radius. Because if it's ionic radius, you have to pick, well, what ionic radius? It's a distribution always, right? In your training set. Copper
Yeah.
can be +2, +1, 0, or even -1. And there's some distribution there. Anyway,
Okay.
this was another paper by, published recently from the team of the prodigies of Ichiro Takeuchi, J. Hattrick Simpers, Brian DeCoste, and others. A great piece of work of very little of the right data is needed to predict materials properties accurately. And here, instead of showing the number of epochs in training, I'm showing the number of added data in training. And I don't know about your team, but in our team, we love competing against our machine learning model when it's training. And we pause it at various points and we'll say, okay, it's trying to train off of indium arsenide. What's the band gap? And then we'll sit around and say, oh, indium arsenic, pretty big atoms. I'm guessing it's a pretty small band gap, 0.7 EV. And we'll play these games to see at what point does the machine learning algorithm start to beat us. And I have to say with humility, it's not very many epochs. It's not very many number of added data before the ML algorithm outperforms me in predicting some of these materials properties. Next slide. So it's a question of the right information, the right data points, the diversity. This was an interesting paper that we did with Guy Bazin, formerly in the UC system, now in Singapore at NUS, where we were trying to predict the antimicrobial activity a very complex property of a candidate antibiotic molecule. So it's essentially the concentration at which a population of bacteria drops by a factor of 2. So E. coli, for example, what is the antimicrobial activity of this molecule? And it turned out that a combination of very crude zero-dimensional scalars like topological polar surface area and others called Mordred and Morgan descriptors was sufficient to predict some pretty complex behavior. This is not a ground state property of the material. This is something different. Next, involving charge transport, right? Next, and then next slide, please. We had a really interesting study where we were not only training FDCP to predict new materials, but we were also doing a bit of transfer learning, unpublished work by Danny, where we were trying to predict some more advanced properties of solar cells like open circuit voltage. So next slide. In that study, we had 70,000 crystals with known band gaps, 80 experimental open circuit voltages of solar cells, and 3,000 experimental band gaps. So essentially a ground truth on the predicted band gap from Materials Project DFT with a coarse grid. Next slide. And the transfer learning was basically, if you train with Materials Project and you train only a subset, 80 compounds with the experimental VOC, can you then back propagate to the entire set of 70,000 Materials Project materials and predict what the VOC would be? It's similar to the ICSD score trick that we do, where we back propagate based on a subset of materials. We back propagate that property to the entire set. And interestingly, on the next slide, this material or this device property, VOC, which depends on so many things. It depends not only on the fundamental physics of the materials, but it also depends on the operator, how skilled they are, how, the equipment, defects, the humidity of that day. But nevertheless, the algorithm was able to propose things like cadmium telluride should be a good solar cell material. Gallium arsenide should be a good solar cell material. And yeah, there's a lot of junk in here. But if you consider a hit rate, even in this small subset of compounds, tin sulfide, there's a few of them. It was really stunning. And it kind of opened my mind to, there is mutual information passing between these different properties and representations that somehow link to the engineering parameters of merit that we care about, however weakly. And as in terms of a guide, if our throughput continues to increase, our predictor doesn't need to be perfect. It just needs to be good enough, matched to our throughput, to have a few hits to keep us moving in the right direction. So next slide. Conclusions. I think we're ready to wrap it up for today. What features are necessary to predict materials properties? Depends on your approach. It depends on your background and your training. But often, simpler features tend to be rather good. Simple properties and simple representations tend to be rather good inputs to predict properties, and even perform generative or conditional generative design or inverse design. Raul could give his conclusions next, but I'll just end by saying, stay curious about how emerging machine learning algorithms process information. How do they encode the information? How do they pass it through? How do they link it in training? Because I think somewhere inside of here is a challenge to our own human understanding of what is a material. In 2025, we think we have it all figured out with Schrodinger's equation and chi-squared distribution of electron wave function. Maybe we don't have everything figured out quite yet. Maybe there's still some mysteries out there, but I'll pass it off to Raul to share his thoughts before we break for questions.
Yeah, thanks, Tonio. Maybe I want to show you, I want to show just one picture, one of the slides that we skipped, but I think it's especially revealing, or it summarizes the idea pretty well, which is this thing, right? That we tended to think that representations were actually maybe the material, or really close to the material, and we didn't think about them as just other properties. And I think when you start thinking in those terms, I think a lot of mysterious empirical results in our field start to at least start making sense within this framework. They are a bit coherent. So I think more work needs to be done in this direction. Yeah, I would love to hear what you guys think.
Thank you very much, Tonio and Raul, both of you, for the very insightful presentation. So please thank our speakers today, physically or virtually. I'll stop the recording.